AWS What's Next. We're talking to John Handler and Vigya Sharma about the latest Autotune feature launch for Amazon Elasticsearch Service. John, Vigya, thank you so much for joining us today. I know this is a very exciting launch, and we have lots of silly and uninformed questions that hopefully you are the experts that are able to answer for.
Yeah, absolutely. Thanks for having us.
Yeah, thanks, Nick. It's fun to be here.
Maybe we can start out just by sort of addressing a high level, like auto-tuning is a feature that makes running Elasticsearch, Amazon Elasticsearch service, sort of a lot easier, especially at scale. You know, as you run Elasticsearch, your workload is going to grow, and eventually it becomes challenging to figure out exactly how to scale it and what hardware you need and how to deploy it. So with auto-tuning, we're really trying to start taking that burden from our customers and really bringing them something that's going to be adaptive to their workload and make it much easier to run at scale.
Yeah, before we go further, John, can I ask a really dumb question? What is Elasticsearch?
Oh, sure.
And,
yeah, sure.
Oh.
Well, I mean, I brought some slides to point at. I could put those up, or I mean, I'm happy to talk off the cuff too. Fundamentally, with Elasticsearch, up to you guys.
Feel free to throw them up, and we'll just click through them as you want, and we'll continue to pester you with simple questions. Oh, we lost him. All right, well, while we're waiting for John to reconnect, he may have hit the wrong button there. He accidentally hit the trap door. So Vigya, while we're waiting for John to reconnect, do you want to talk a little bit about Elasticsearch as sort of a precursor to the Autotune feature?
Absolutely. So Elasticsearch it's a powerful tool for search and log analytics. And the managed service, which is the managed Amazon Elasticsearch service, makes it very easy for you to host this distributed system on the cloud and to manage it. And we have customers who use Elasticsearch for a variety of reasons. Looks like John's about to get back on, but continuing with that train of thought, we have customers who use it for curated search, people who use it for log analytics. I'm going to let John talk. He's the expert in these things.
Yeah, that was super awesome. I managed to hit exactly the wrong button, which I told myself, don't hit that button, right? And so I managed to do it. All right, back now. And I'll just sort of pick up from where that conversation left off. You know, as we look at Elasticsearch and what is it and what do people do with it, we fundamentally have two workloads. Elasticsearch itself is a search engine technology. And so we're all very familiar with search. Search has become ubiquitous. And as we interact with the applications that we use, we're constantly jumping to search. I don't know how many of you have wandered around in your kitchen wishing for the search box so that you could find that one, implement that you really need to cook this meal, right? So that's our first search workload. Load your data in, search it, gives you rich query language, adjustable ranking, language features, really natural language processing for full text search. And then, as Elasticsearch has grown and developed and has been out there, people really started to throw log data and other sort of streaming data in there. And a whole sort of ecosystem and environment around log analytics rose up around it. And Elasticsearch, along with some companion technologies, Logstash and Kibana, give you the ability to ingest data in near real-time log data, metrics, traces, and build visualizations on top of that dashboard to understand what's happening with your infrastructure. Security is another very common analytics workload where you're looking at interactions with your application and figuring out fraud or other denial of service, those kinds of things, right? So we have these two kind of patterns and use cases that most people are doing. So, from the high level, we really want to dig in because as you know, or as I said, like auto-tuning is a very low level kind of tuning. And so we're starting with the 30,000 mile view, and we're going to zoom in really into sort of all of the hardware and how the whole thing works, so we can get to the demo and sort of have an understanding the changes here, which are really profound, and they're super great. So yeah, go ahead.
Yeah, I was just gonna ask a semi-informed, but again, classic naive question here, and it's largely that with as with most applications, as you scale them out, and scale means a lot of different things. When you mention the word search, I'm thinking of things around the size of the data that I have stored that I want to search within. I have ideas coming to mind about the access patterns. Are there hot or cold parts of my overall data set? Are there spikes in how I'm querying that data? I'm thinking of is compute a bottleneck at certain portions? And so when I'm thinking about running an application for Elasticsearch, even if it sounds like something as simple as storing and searching my data, I can start to think of a million different ways in which it is difficult to find out exactly how to right size that cluster. Maybe I'm jumping the gun with this question because that's exactly what you're showing right here, which is really the use case, and you're probably going to dig into that. So if I'm asking the question you're about to answer, just ignore me and go on.
No, not exactly. I mean, I would say that this is a very common sort of customer issue that we run into. Elasticsearch is super simple to get started, but as the size of the usage grows, as the amount of usage grows, it can be very difficult to right size it. So I'm not going to go through a lot of right sizing best practices, but I will, just to give you a feel, in a search workload, we would say usually 50 gigabytes to 100 gigabytes is a very common sort of amount of data, with queries that range in the, up to the hundreds per second. At the very large end, they can get into the tens of thousands, but commonly in the hundreds or so, with a much lower indexing kind of footprint. And then with a log analytics workload, we can see tens of terabytes per day on the ingest side, where the queries for that is really driving a few dashboards, and there's very light query load. And in both of these cases, you have a different footprint and a different way that you have to look at sizing and capacity, because they drive different resource usage. So it's a very complicated topic, and it's even more complicated in that the actual workload has a big component in terms of what is the resource demand, right? Down to what is the data itself, how Elasticsearch processes that data relates to the content that you're actually sending to Elasticsearch. So it's a complicated topic, and I'm going to brush lightly over it. Fair?
Yeah.
So with the interaction, the interaction, Elasticsearch is really at heart a database technology. I'm a search technologist at heart, and so in some ways I don't like to reduce it down to just a database. It's a database technology that is not a relational database, not a NoSQL database, but it is a database kind of interaction. And I just want to give you a feel for how do you interact with Elasticsearch. And you can see on the left here, we have our two different workloads. We have our server and application and networking, all the log data for the log analytics workload. And we have our application data if we're doing like e-commerce search, or we're doing some location aware application that needs to search by location. That's going to come usually from a relational store or perhaps a NoSQL store. All of that data has to get formatted as JSON. And within that JSON, you're going to specify a set of fields and values, right? These are JSON keys and JSON values, can be nested down to and different levels, but it's going to be JSON. Elasticsearch is a REST technology, so you use REST APIs to communicate. You send that data for indexing to the Amazon Elasticsearch or to the Elasticsearch cluster itself. Everything gets indexed, so all of the fields are searchable within the JSON, and you can, including down to the nesting level. On the query side, very common, you have a REST API, they're JSON-based queries. You send those queries to Elasticsearch, and Elasticsearch is going to respond to that query. So really familiar sort of interaction model. It's send your data in, it gets organized and indexed, you query against it, right? Under the cover, Elasticsearch is a distributed technology, right? So now we're starting to get into sort of the details and where the scaling comes in and how it's important to think about it. So when you use Amazon Elasticsearch service, you deploy what we call a domain. That domain is going to wrap a set of software and hardware to provide Elasticsearch REST APIs to you over an endpoint, which is a DNS entry. It's just a domain name. That's where you send your REST API calls. Under the covers and within the service itself, we deploy into a service-owned VPC a set of nodes that perform various functions for the cluster. The ones we're going to focus on really are the data nodes. So the data nodes are where the indexing occurs, where the indexes are stored, and where the queries are processed. You're going to select, when you use Amazon Elasticsearch service, you're going to select a set of instances to deploy as data nodes, right? So you're going to say, give me 5 R5 12x larges. That's where all of the processing will happen on those data nodes. Obviously, those data nodes have characteristics in terms of CPU, storage, memory, all of that you can use this level of description to try to address the resource needs for your workload, right? So you can deploy more or fewer data nodes, and that's one way that you can right size for your particular workload. But it's a pretty blunt tool. So you can look at some of the KPIs that we send as metrics, and you can make some decisions. You can say, okay, yeah, well, it looks like our CPUs are running really hot. We need to expand our CPU capacity, so we're going to add more nodes, right? This is not the level where that auto tuning addresses. We're looking at a layer below this. So we still have to go peel back a little bit farther. But yeah.
Is that the Open Distro for Elasticsearch logo I see there on the data nodes?
It is the Open Distro for Elasticsearch logo there. There's multiple layers of security. It's in this diagram to point out that we actually use the Open Distro security plugin to support the security model of the service, right? It can be a little bit confusing. The service itself is not Open Distro. Open Distro is a project. The service is a product that is running partially the plugins from Open Distro along with native open source Elasticsearch, right?
Yeah, and that was a great overview. I know we don't need to really dive too much deeper there, but I do have one question from Twitch chat here that's relevant on this slide before we move on. And that's from Hydro KK. They're wondering, what is an ultra warm node? And I know this is something that was new as of reInvent 2019, if I remember correctly. But John, I know you're the expert there.
Yeah, 2019, I think. Yeah. So one of the characteristics of Elasticsearch is that the cost will tend to grow linear with the amount of data that you're putting in. And especially for log analytics, we see where we have those tens of terabytes up to a day, we can see the cost grow very quickly. And we heard from our customers that they really wanted to be able to hold more data, but it wasn't cost effective for them. So we designed a solution that uses S3 as a backing store within the service to reduce the cost of holding that data. The trade-off is the latencies are going to be higher, and we have all kinds of things that we do to improve the latency over sort of raw S3 searching, but the latencies will be higher, but the cost is dramatically less. So you can see a cost reduction over the long tail of data of up to 90%. We see a typical cost reduction, 90, not 19. So we see a typical cost reduction in the 40 to 50% range for data that's stored in ultra-warm versus hot data nodes is what the normal ones are called, right? Awesome. I encourage you to go check it out. It's a really cool feature. Like I said, it does enable retaining more data and the ability to interact with that data for a longer time period at a dramatically reduced cost.
Just hearing all of the
crash course on. We've got some latency today for some reason. We keep talking over each other, but I'll go first here. Yeah, thanks for the crash course in Elasticsearch here. Can you? Obviously, there's so many different ways to use Elasticsearch. Can we kind of pick one. Maybe we can talk through a customer use case. Like what customer is using Elasticsearch on AWS, and then what kind of scaling challenges are they hitting? And then we can kind of tie that into how Autotune helps that use case.
Yeah, sure. Why don't we talk about a log analytics workload? One of our customers is Autodesk, and they've built a solution that enables them to centralize logging across multiple applications and multiple AWS environments, bring that all into a central location, and then provide single pane of glass, as well as the ability for each of those groups to use Elasticsearch dashboards in Kibana to see what's going on with their application. So that's a very typical workload. And the log analytics workload, well, we have to go down a little bit to understand a little bit more about sort of the scaling challenges for that. So maybe let me just talk about a little bit about indexes and shards. So when you use Elasticsearch, you're using those REST APIs, you're sending your data in, you send it to an index. You can make the analogy that an index is a lot like a database table. And so it's not exactly the same, and it's not the same as a relational database table, but you could think of an index like a table. We have our document here on the left. Document is like a row in the table. And then we have our field value pairs in the JSON. Those are like the columns of the table. So index itself is sort of a logical high-level structure. In fact, your index is partitioned across a set of shards. So when you create that index, you specify the shard strategy and you say, I want 5 shards here. Your data that goes to that index is randomized across those 5 shards. I'm going to do 3 slides real quick. Elasticsearch then is going to distribute those shards to data nodes, right? So if I have a 5 primary shard index, primary just refers to the partitioning. I can also have replicas. Elasticsearch is going to distribute those shards onto the nodes that it has available as evenly as possible, and so that no primary and replica goes onto the same node. When we get to query processing, the requests come in, or even indexing, the requests are going to come in. Some node will catch that request and act as a coordinator and distribute it to all of the nodes that have shards that need to process that request. It's an indexing request. If I have 5 primary shards, it's going to land on a node, get forwarded to 5 other nodes or however many other nodes, and each shard is going to do the work of indexing that data, right? The specific subset that goes with that shard, right? So that's the basic processing. And then what I wanted to do is actually peel back even one more layer so that I can talk a little bit about the underlying technology, right? Underlying Elasticsearch is a technology called Lucene. Lucene is an Apache Foundation project. It is a Java library to read and write search indexes. And Elasticsearch at the shard level conceptually is an instance of Lucene. So Lucene is actually doing the work in Elasticsearch. When requests come, Lucene is going to build a per field index for each of the fields in the document, right? Now that index is actually on disk. Lucene is a disk-backed technology, right? So we have the fields are actual files in the file system. And when Lucene needs to do work, it's going to access the data structures through memory mapping, right? So we have our fields, all of the index structure is sitting on disk. The file system is going to swap in pages of that. So we have our file system cache. And then we have our Lucene layer where the actual processing is happening on those fields. Along with that, within Elasticsearch in the ES process, we have some caches. We have field data caches, query caches, filter caches. We also have some queues. So we have bulk queues, we have search queues, merge queues. All of these are sort of on each instance, how Elasticsearch is interacting with the low-level parameters. It's a lot to take in, and I tried to brush through it, but please let me know if that doesn't make sense, because this is where auto-tuning is going to come into play in this layer.
Yeah, I think it makes a lot of sense. And to your point earlier around like we won't go into all of the best practices of optimizing the system manually, that's for good reason, right? Like something like Amazon Elasticsearch Service already helps to manage some of this, but what I'm imagining we're really going to look towards here is Autotune for Amazon Elasticsearch Service to handle a lot of this for me. And I have a really great appreciation here for how many layers of complexity there are to really getting this right. I'm imagining folks like you and Vigya here have really gone deep in the weeds with this. I mean, you're explaining to us right now. If I just want to be able to search and index my logs or a variety of like maybe I have an inventory and a catalog that I want my website to be able to be backed by, I don't want to have to think about how Lucene is going to interact with my file system, right? In essence, that's what we use managed services for broadly, right? And now auto tuning on top of that seems like it would help to make even more of these problems go away.
Yes, absolutely. I was trying to get back to Rob's question a little bit, and I think if we look at sort of your typical log analytics workload, and especially one that's a centralized one, fundamentally what you have is a number of different indexes that are all active at the same time and realized as a set of shards that are all active at the same time. And we're looking at single shard here, right? So the complexity comes when you start to deploy multiple of these indexes leading to multiple shards, and the interaction between all of those is is really complex, right? And so to your point, you don't want to think about that. You just want to use the index. You just want to like have the visualization on the screen, not deal with all of this stuff. So I'm going to pass off to Vigya because Vigya is going to take it from this point to talk about what we did with auto tuning and what we implemented and how we did it, and demo too.
Absolutely. Well, first of all, thanks, John. And this is amazing depth. I'm pretty amazed by the amount of content you can cover and put so simply. It took me a long time to learn and figure out these things. Let's talk about Autotune, right? But before that, let me preface it with something that is kind of obvious and we all know there about AWS Cloud. The managed service is already making things simple, right? These things are hard. It's hard to figure out the hardware you need. It's hard to figure out how the internal data structures should be. But when your workload grows and as you get more production traffic, you can always throw more hardware at a problem. You can, with a few clicks, you can add more machines and your cluster scales, you have a performing cluster. But Nick talked about money in the wallet earlier, right? And we know from years of operating cloud services and from lots and lots of clusters that we've operated, that as your workload grows and as your production traffic evolves, in fact, as your data evolves, as you get more serious about Elasticsearch, it develops a unique resource footprint. A search use case, John just described, that will demand different parts of the internals of this distributed machinery than, let's say, a log analytics use case. It has a unique resource footprint, a unique signature, if you will, right? And if we can tune the internals of Elasticsearch, the internals of the Java virtual machine, which is running Elasticsearch, to meet the demands of your specific workload, then it has significant performance impact. And that right there is what we want to do. We want you to get the best value from the hardware you already have before you go ahead, make those clicks and increase your cluster size, right? Because that is where you're getting the best performance and the best stability that's possible from your hardware. That's where Autotune comes in. So I'm going to take over the screen share, John, and I'll quickly share a small infographic which talks about what Autotune really is. Let me get to the infographic. All right. So Autotune is a closed loop control system. I know Nick also talked about a control system in his own room with the GPU and the heating kind of making things work. This is a feedback loop and it self-adapts to the unique requirements of the workload that I just talked about. Now, how does a feedback loop work? it obviously starts with observability. You need to know what's happening in your system. But we are talking about deep telemetry here. These metrics are collected every few seconds, and it's collected across a variety of things. These are collected for every node in the diagram that John just showed, but also for every shard, for every index, and for every thread that is going on inside your cluster. So Autotune essentially knows what kind of resources, what internal data structures is each operation that's going on in your cluster. How much does it consume? How much CPU do you spend on a specific operation? Which queues are required more? Which data structures and caches are required more? And then all of this data is fed into decision trees. Again, the decision trees are distributed across different nodes. So every node can also make a node local decision. For example, your shards may be placed, your shards are essentially placed across different nodes. And maybe some of your indexes get more traffic, more write traffic than some of the other indexes. And those nodes need to be optimized and tuned differently from some of the other nodes. So Autotune is capable of doing that, making node local decisions, but also putting it all together. So all of this information flows into the leader node, and the leader node puts it together. It looks at everything. If as a human, I were to tune my cluster, and if I were to optimize for my use case, I would probably run a few tests. I will look at a few metrics that are out there, things which make sense to me. And based on some parameters, I would optimize my cluster. But that does not factor in everything that is out there. That does not factor in the internals of ElasticSearch and the internals of JVM, which could have been considered. Just the sheer volume of data there is mind-boggling. And you need an automated system which can look at everything. So you don't want to optimize for performance while your servers are melting down. You don't want your website to go down, right? You want availability and uptime. And that is what Autotune takes care. It will always prioritize stability over performance. And if it makes sense to optimize something, that's where the optimizations get applied. And once optimizations are applied, they make changes to your distributed system. Again, those changes will get reflected in metrics, and that's where the loop closes and completes. And there you are looking at it all over again.
Vigya, I have a maybe naive question again, but from what I'm hearing here, and again, John walked us through all the very different layers to Elasticsearch, and then the Amazon Elasticsearch product, and then the deployment infrastructure that a user chooses to run their configured Elasticsearch cluster on. What this sounds like to me is that while there were settings that a user could and knobs they could tune with regards to like cluster configuration broadly, like the instance type they want to deploy on and the number of nodes, this feedback loop addresses a much deeper set of knobs in the Elasticsearch service, or the Elasticsearch application itself. And you're talking to things like JVM memory pressure, for example, and not only does it enable that optimization, but it does so automatically. Is that the scope of what this feature is going to work on?
Pretty much, Nick. That is spot on. So yes, it looks at internals of Elasticsearch. Some of those are knobs that could be controlled. Some of those are not even knobs. They are hooks which Autotune is hooked into, and so it can control. And while we are on that topic, let's talk about what is Autotune really looking at in this version, right? So these are all the things which Autotune can tune today. Now, one of the asks we got from our customers and from looking at all the clusters that we have is around memory management. Memory management is a very important topic for our clusters because you have limited amount of heap that is available. And even though you can add more hardware and you can add more RAM, effectively managing that really affects the kind of performance that you can get out of your cluster. So there's a few things which Autotune looks at. The first of them are queues and queue sizes. John talked about the search queues and the write queues. These queues are essentially buffers which hold your requests before their corresponding threads pick them up and execute them. And when your requests are full, you get rejections. Now, typically those queue sizes are defaults, and they would work more or less, they would work pretty much in a standard situation, but we're not talking about the standard situation here, right? We're talking about what's good for your particular workload. Perhaps for your traffic, a larger search queue, because you are a search only workload, would make more sense. Now, rejections are not bad. They protect your cluster. Otherwise you just have a lot of requests that are pending in your memory while your servers are just busy with other operations. So rejections are important, but having a fixed queue size kind of misses the point, because now you'll have rejections for even though your cluster could handle more requests. And on the counter side, you might keep requests in your queue even though your cluster was unstable, and you could release more memory and more heap to help with some of the other operations. While we are on topic of queues, this is what I would also like to show today, give our viewers a taste of what Autotune looks like. So let me quickly jump over to the AWS console. And this right here is the AWS console. Phil showed it earlier. This is what it looks like for Elasticsearch service. Here I have created a domain, and this is an existing domain. So some of our users who used Elasticsearch are familiar with this screen. They'll notice a new tab here, which is Autotune. And for right now, I've disabled Autotune. So for an existing domain, that's how you would see it. Autotune is disabled. There's also this notifications tab, which doesn't have any notifications right now. And I'm going to quickly jump to another screen and fire some traffic on this cluster. So this traffic that I'm sending to this domain is purely write traffic. And I'm deliberately sending a lot more requests than what this cluster can handle. And while these requests reach and it warms up and we see some of the rejections, let's talk about some of the other things that are here, right? So field data cache and shard request caches. These are two caches available again within Elasticsearch. Your field data cache helps with aggregations. John talked about field values that you provide that are like columns in the database analogy. Field data cache helps you aggregate and speeden up all your aggregations. Shard request cache is the quintessential cache that you can imagine. If you have requests that have been answered before and your data has not been updated, this cache will give you better tail latencies. And then the JVM generation sizing and JVM heap sizing, those are interesting ones. I mean, everything is interesting, but those are more involved because they are outside Elasticsearch and they lie in the realm of the Java virtual machine.
So
did you have a question there, Nick?
Yeah, just for my own curiosity here. So what we're seeing now is you had in the console there an existing, it's a domain, but it's essentially an Elasticsearch cluster that's back behind this domain, and we are hitting it with a particular workload, and obviously we know that this is substantial enough to be able to stress the cluster. Now, can you talk a little bit about, we don't maybe know how it will stress the cluster. Why don't you tell us a little bit about the requests that you're sending, and then people at home or in chat can hypothesize in which way it will stress the cluster and how it will try to scale to account for it.
Absolutely. So this is all write workload, and these are all write requests. People who've used Elasticsearch before are familiar with the concept of bulk requests. Bulk requests essentially batch together a certain kind of requests in a payload and send them. So these are all bulk requests which contain write operations. And again, folks who are familiar with Elasticsearch would know that this should stress the write part of your Elasticsearch machinery. So it should overload your write queues. You should probably see some rejections if my demo works and if we are able to fire up enough traffic. Fingers crossed. But yeah. And then coming back to talking about the JVM, right? So we all know Java is garbage collected. And we know JVM does a lot of stuff to make garbage collection optimal. The way it does that is by separating your objects into short-lived and long-lived objects. Now, garbage collection requires JVM to step in, take hold of some of CPU cycles, and sweep away all the objects which are not being used. And if you can partition your objects into short-lived and long-lived objects, which the JVM does by splitting the heap that's available to your application into different partitions, which are called generations. So there's a young generation that's available for short-lived objects and an old generation which is available for long-lived objects. Now, what size should you give to your young and old generations? That is very specific to your workload. I mean, quick question. Can you tell me how many short-lived objects does your workload generate? I mean, what are we even talking about, right? How do you know what kind of short-lived and long-lived objects are being generated? Autotune looks at all of that. Autotune knows exactly how your data structures live, how long your objects live, and how much of your objects are promoted across generations. So they'll first fall into young generation. After they've been around for some time, the JVM will promote them to old generation. And each of these generations have different garbage collection cycles, which will result in either a minor or a major pause. Basically, it's asking for CPU to free up your heap. And where does it get that CPU from, right? It'll take it away from some of the other applications that are using it. Sometimes it might need to stop the world and pause all the other threads before it can do garbage collection, but that's pretty much what it does. Now, Autotune can figure out the ratio of short-lived and long-lived objects. It knows how they're being promoted. It knows how much CPU is being spent on GC. It's looking at all of these things. And it also knows the kind of workload you have. And it can size the ratio of young and old generation to a ratio that best fits your workload. And when you do that, you have much more optimized garbage collection cycles, which means a lot more CPU is now available to what you're actually paying for your workload, right? So that's an interesting one. And then you have heap sizes. Sometimes we figure out that just changing the generation ratios are not enough. Maybe your workload demands more from your cluster. And so you need a larger heap. And with a larger heap, you possibly need a different garbage collection algorithm to run. And those are the things which Autotune would do if in the JVM heap size action. Then of course there's, yeah.
These are all making my head spin with all of the different ways, the underlying properties that you can configure with ElasticSearch. So we're throwing a load at an ElasticSearch cluster. Obviously, you know, if the experiment works, we know that it'll stress it sufficiently that it should cause some sort of change event or autoscale with Autotune enabled. But let's assume that I am someone who doesn't understand much of this at all, but I'm using an Elasticsearch cluster. What should I start seeing? Is there anything over in CloudWatch that I would be potentially able to look at and say, oh, wow, there's some problems going on over here?
Absolutely. That's a very good segue to some of the things that I would like to show. Let me just quickly finish with the cache clear action as well. That's a final remediation where Autotune realizes that freeing up and reclaiming some of the heap that's available with caches would save your cluster, and your cluster is about to go under and it's about to crash. So you need some memory, and it gives it that breathing room before your system crashes. Like I said, we always prefer stability over performance in Autotune. And with that, let me get to your question. Let me quickly jump. Oops. Give me a second here. And well, you talked about security. There's a security for you from AWS. We don't even keep our sessions alive for long. So while this loads back, let me share something else. Let me talk about how is it doing in production. So all of this is good. We can fire some traffic. We can talk about things which we've cooked up in the demo. But let me talk about what it does on an actual production cluster. So these are stats from real customers and from real workloads that we've seen on production. Now, this was one cluster where the JVM generation sizing auto-tuning action took place. This graph right here is the JVM memory pressure graph. And this is one of the signals which customers who are using managed Amazon Elasticsearch service can also get to see when they find Autotune taking effect and taking actions on their cluster. So you have on the y-axis a percentage of heap that's already being consumed. And x-axis, of course, is time. And as you can see, as more and more objects collect, your usage rises and your memory pressure rises. And then it hits a particular threshold around 75%. at which garbage collection sweeps in, and that's a major garbage collection. And your data is collected, reclaimed, and so your memory pressure falls. And this gives rise to a very characteristic sawtooth pattern in your JVM memory pressure graph. Your data will get collected. It will go all the way to the threshold. That's where JVM realizes, okay, stop. You have absolutely too much of your heap used. And before you can go further, I really need to clean it up. Stop everything else. Let me just clean it up, give you back some heap. And so you can continue with your workload. Now, right about here, where you see the line go flat, is where Autotune configured generation sizing ratios. And it tuned your young generation and old generation to a better ratio for this workload. Now, as you can see beyond that, and this is across multiple days, so it's not just an overnight traffic, you can see that even though you're still firing requests, it's not really hitting 75%, or it's not really hitting your threshold that quickly. And even though you have garbage collection happening at the back end, you don't really need all your major stop the world pauses anymore. It's a much more stable cluster. And for the same cluster, we talked about Autotune knowing how much CPU you spend on an operation, right? And if you freed up your CPU from garbage collection, you have more CPU available for all the good stuff, for everything that John talked about, and for everything that you paid AWS to host an Elasticsearch cluster for. So right here is, yeah, Nick,
Yeah.
I see you have a question.
So I just want to make sure that I understand this very, very particularly. When we look at this Elasticsearch JVM memory pressure graph over time, there was not a hardware like scale up event, right? There was not, hey, let's move to a bigger instance.
Not
This
at
was
all.
entirely auto tuning of the application configuration without like application downtime, for example, right?
Exactly. And that's the beauty of it, because in a universe before Autotune, if I had this cluster, I would look at it and I would say, man, we are hitting the threshold so frequently. Let's go to larger hardware, right? And yeah, it's super simple, but then it costs more money. So there was no hardware change. This is purely changing the ratio of your generation sizes, and that's the kind of impact it can make on your resources. But why just memory pressure? We spoke about garbage collection stealing away your CPU cycles. So for the same cluster, let's look at what CPU looks like. Now I know the text might be a little blurry, so let me walk you through what this graph really means. So this graph here is a split of how much CPU is getting spent on which operation. And the green lines here are garbage collection. And then the pink and the gray lines is your read and write workload. And for this particular instance, both of them are read workloads. They are different parts of read. So like I said, the telemetry is pretty deep. I won't go into too much details, but even your reads,
Yeah, no. So just so that again, this makes sense to me. We just saw that we had a significant reduction in garbage collection events, and that was just, we were basically just getting way more juice for the squeeze out of our given set of hardware. And so on this flame graph, we see again green for garbage collection and pink and like dark gray there at the top as read and write events. So if garbage collection is let's say like wasted heat energy or wasted resources here, we want to be able to find ways to minimize time spent on our CPU on garbage collection. Is that correct?
Yes, exactly. Of course, garbage collection will happen. You're using your Java virtual memory, but you want to reduce the CPU that is spent on it. And if you see on the earlier parts of this graph, there's a lot of green. And while usually green is good, it's not so good here, because this is all the garbage collection that your JVM is doing and eating up on your CPU. And if you see a light faded gray vertical bar here, it's also where the tooltip for the graph was. After that R is when Autotune had taken shape. And that's where you have a lot more CPU available for your reads, and your garbage collection really reduces the amount of CPU that you spend on garbage collection. Here's another quick one. And this one here is a change in your heap size. Again, there's no hardware change that happened here. But for the same hardware and for the same amount of memory, Autotune changed the amount of heap that was available to your cluster. And so it decided that, well, you can't change generation size ratios here, and that's not going to do you any good. You have enough RAM available. Why don't I give you more heap and switch you to a different garbage collection algorithm that works better for that heap size? And that's exactly the event which happened here around Feb 24th. And again, there's a reduction in memory pressure after that. So this is how the entire thing plays in. These are all graphs from actual production workloads. Let's see how our domain is doing, right? So, okay. Well, thanks to security, we were signed out. Let me sign back to the AWS console real quick. Okay, here we are. So if you remember, the Autotune was my domain, which I was showing earlier. And again, this was a domain where Autotune was not enabled, right? So I have an existing domain. I don't know if Autotune will do me any good. What's my touch point here? What's the user experience here? Now, because of all the workloads that we've been firing, Autotune sees there are rejections, and it realizes that there's an optimization it can make that can do you some good. And even though you don't have Autotune enabled, it'll send you a gentle notification. So in your notifications tab, I see a new notification available. And this new notification here says that Autotune recommends new settings for your domain, right? If you click on this notification, it, of course, it has an acknowledge button, so you can remove the noise, but it also has an enable Autotune button. Now, when I click on this button, it takes me to a screen which allows me to modify my domain configuration and enable Autotune. When you enable Autotune, you give it a few inputs. Of course, you enable it. And you can also add a maintenance window to it. Now, there are certain auto-tuning actions which apply at a node level and which can dynamically update the size of data structures, and you don't really need a JVM restart. But if you're changing some deep JVM settings like your generation size ratios, or if you're literally adding more heap and changing the garbage collector in your JVM, then you need to redeploy. And that is all handled by the managed service. When that happens, there is no disruption, there is no downtime. But even then, we would want you to have control over when such a major event kicks in. And while there's no availability loss and there's total complete uptime, when this happens, maybe you don't want it to happen during your peak workloads. Maybe you want it to happen on a weekend, on a Saturday or a Sunday, when you have lighter workload. And that's where you can specify a maintenance window. So if you have a maintenance window, you can give it a duration. Let's say I give it a duration of 2. You can give it a recurrence. So you can say repeat it every week on Sunday. Let's say I wanted to kick off at 10 a.m. on a Sunday. Now, if there are these JVM tuning actions that are available, they will only be initiated during a maintenance window. You will never have an out of turn JVM scheduling action kicking in. And JVM scheduling action goes through a blue-green deployment, so you don't have any loss of uptime or availability. But even so, it'll only go in through during your maintenance window. Well, that's it. You enable it.
Yeah, I was just gonna say, to make this tangible in a way that like it would impact when I would want to set my maintenance window. Obviously, maintenance windows during the greatest lull in your traffic probably make the most sense. But you mentioned there's no service disruption. So what is the purpose of setting a maintenance window? I think it really grants you, in my opinion, the peace of mind that if I am updating during a given maintenance window, that update may not be sprung. Let's say I run an application backed by Elasticsearch, and I am going to expect, or even don't expect, a surge in traffic all of a sudden. Now, even though there's no service disruption, all those requests could be enqueued, and then even though they're not lost, there could be a higher latency on those responses. And so that's what this maintenance window helps to solve, right? You do the maintenance and those updates when you know it will minimize impact on latency or anything, so that when you have expected or unexpected traffic spikes, that won't sort of align with the update, even with blue-green deployments and no like full service loss.
Yeah, well, that's exactly the way to put it, Nick. So again, spot on. Yeah, this is more control. You want control over your clusters. You want to know when will maintenance happen and when will it not happen. So this gives our customers some say over that. And that's pretty much it. I know we went into a lot of details around how you see in a structured, Elasticsearch is structured, and all the JVM and queue related stuff. But this is a managed service. It should not be so hard for you. You should not have to really think about these things. And that's what is happening here. All you need to do is enable Autotune. If you don't enable, you'll see a notification. Pick a maintenance window that works for you, click submit, and Autotune will get enabled. Going back to the tests and the demo that I was talking about, right? So, well, it added some rejections, and those rejections triggered Autotune to actually suggest that you should enable it. Now, after Autotune is enabled, it'll monitor, and if that pressure persists for some time, that's where it'll go ahead and apply your queue tuning. But I can show what it would look like. So this right here is this right here contains some graphs from another domain where I've run the same test just because of the timelines of the show that we have. I want to show what it actually looks like and what it would do to your graphs. So we got notifications for Autotune having an action available for you. But how do you look at it historically? And if Autotune was enabled, how do you know that something was done on your cluster? So for that, there is a new metric which the service exposes via CloudWatch. It's called Autotune succeeded. I've just plotted it into a dashboard right here. And as you can see for this cluster, this metric had a value of 1, which means there was an Autotune action that happened at this particular time. Now this graph to my left, the first graph on this dashboard, is about write thread pool rejections. Like I said, the workload was pretty much around write traffic. And when it stresses your cluster, you have write rejections because, well, you have a limited write queue. So the blue line here shows your rejections. And as you can see, your rejections pretty much stabilized after a particular point, right? Now that is where Autotune kicked in and it stabilized your rejections. So if you were to correlate along these lines, your Autotune kicks in. If you can see a dotted line on my dashboard, because it correlates all the 3 graphs together. So this right here is when Autotune kicked in. And after that, your rejections. So before this, you did not have any rejections in the graph, right? So your rejections had spiked. Now this is happening at a very quick time window. So it's a little hard to see it here. But you can see that when Autotune happens, your rejections flatten out. So they're not increasing anymore. And your indexing rate right here goes up because you can index more and you can get more performance out of your cluster. So that's
for folks who may not know, the rejections metric is a cumulative metric from node boot. So when you see the rejections increasing, that means you're currently having rejections. When it's flat, you've historically had rejections, but no new ones are accumulating. That's why the line goes flat. That's why we can say that, yeah, historically we had some rejections. Now we have no new ones.
It's
Exactly.
It's super interesting how it's not disjoint, but it's not a gradual evening off of the rejections. And I know that may just be the unique interaction here of the workload we gave it with the auto tuning event, but it went essentially instantaneously when the update was applied from a consistent and sharp increase in the write queue and consequently the number of rejections, and then almost at this like single disjoint moment, the rejections stopped. So really exciting. And again, there on the right, I know it's just one little tiny dot, but when you sort of, if you were to overlay these 2 graphs, you see that auto tune event being executed directly at the inflection point there of when the thread pool rejections stop happening, and therefore the sum of them stops going up. Cool. So
Yeah, well,
I know we talked about
tuning for you.
Yeah, I know we talked about so much here, and I want to, and I apologize, Vigya and John, you're flipped here on the names and overlays, but we've been through enough of the broadcast on this session here that folks will know each of you.
Yeah,
We
I'm Vigya.
I'm John.
yeah, and so John, you showed us so much of the underpinnings and the layers of operating Elasticsearch. There's the if I'm going in like sort of reverse order now. You start with the project that is sort of powered with the Lucene engine and how that interacts with the underlying file system. But wait, that has implications for what type of infrastructure you're now running it on and the configuration of the nodes on the cluster and the different types of nodes, because there's data nodes, ultra warm nodes, and leader nodes. And then all of that has to do, is in relation to, how you've chosen to deploy those nodes, or the Elasticsearch service has deployed those on given EC2 instances in your cluster, for example, right? And I know we just saw the single moment in which this Autotune feature raised the notification and enabled you to just auto resolve, but all of that, was just hitting a button that says enable, right? And so I know we're juxtaposing sort of a world of complexity and challenges against a solution that I know we flew through really the enablement section, but is that really just clicking the enable button on an Elasticsearch domain such that it can solve those problems for me? Because if it is that simple, there is not a single Elasticsearch customer that I will not go to here and not tell them, hi, you need to turn this switch on today. Do I have all of that correct?
Yes, absolutely. And we absolutely want all of our customers to enable this. We think it's going to make it easier for them. We think we're going to bring a lot of stability across the service for everybody's workloads. Yeah, absolutely. I would say the one thing to sort of differentiate, as Vigya was talking about, the JVM tuning that's going to happen in that maintenance window, that one's not going to be instantaneous, right? So that one is going to be maintenance window, and you're going to have a redeploy that you're going to go through to get there. But it's not one that you should think about and say like, oh, I don't want to do it. You should think about and say like, what is the ideal time to do this? Because I think those are pretty dramatic graphs myself. Like when you look at the JVM flattening out, you look at the CPU usage drop almost to zero for GC. Like this is a dramatic improvement that you can have and ultimately get more out of the hardware that you're already using, and hence, lower your cost overall, right? Your price performance is going to be a lot better.
Yeah, we talk about.
That's exactly it, Nick. Well, yeah, I don't want to speak over you, but you got it spot on. The whole idea of Autotune, right, is to make it simple. The reason customers came to managed service was to use Elasticsearch. They don't really want to worry about these details, and that's where it has to be. So it's just a button, you enable it, and this is a game changer. You enable a button, and there's this control loop. There's this organism that's putting together everything and adapting to your specific workload needs, so that you're getting the best out of your hardware just at a click of a button.
I would say that there's also just to think about what is this is version limited, right? So I believe we support this. Is it 7.9, Vigya? 7.9 and forward, or did we backport
Oh no,
it?
we backported it. Yeah, we supported it all the 7x versions. We supported 6.7 plus. So
okay.
before 6.7, we have fewer customers on those versions, but 6.7 plus, this is supported, and you can work with it.
Yep.
Yeah, Vigya, I have a new phrase now, and you reminded me. It's a money in the pocket launch, always one that I know people are excited about. But more than anything, we talk about undifferentiated heavy lifting, and really, I think that's the story here, right? Your development team's time is precious. And at the end of the day, you want to deliver unique value by delivering features and working on net new things for your business, and not becoming more proficient at managing an Elasticsearch cluster. Again, a tool is a means to an end. And if you're spending day in and day out simply becoming more proficient with the tool, well, that's nice, but you're only doing that insofar as there's more juice to be squeezed out of the tool. And so what this shows me is that all of the expertise we have at managing Elasticsearch through Elasticsearch service are now being able to be delivered to our customers with literally a click of a button. And I think there are a lot of Elasticsearch cluster admins out there, or folks that are already using it, that are probably breathing a sigh of relief here. But again, more than anything, I think it just gives you more peace of mind, right? You will not fear maybe some of the complexity or some of the art that has to be mastered to make the most of Elasticsearch, and instead you can dive in with the confidence that using something like Autotune surfaces those notifications to you and can help you sort of front run a bit of those concerns. Obviously, it's reactive to the events that are happening. I shouldn't use terminology like that to preempt an event, but again, I think just drastically simplifying a tool that is extremely powerful but doesn't come without its complexities. But you get the best of both worlds here with Autotune. So thank you again. This was immensely helpful, and I know again a lot of buildup, but really I think it's critical to understand this the stage of the landscape here to deeply appreciate how powerful a one-click solution is here to the auto tuning or to the cluster configuration and application configuring challenge with Elasticsearch.
So we blogged about all these details that we talked about. It's slightly more detailed in the sense you can get perhaps a better flavor of the tech that powers this. So there's that. And well, pretty much click the button.
Yeah.